Last time, what were we looking at? Well, where did we end up?
Talking about the chemical bond.
Yep.
How you could represent it.
Yep, we were talking about the chemical bond, and we were coming up with approximations on how to describe molecules rather than atoms. So previously we have looked at hydrogen and helium. Now we're actually going to look at some real stuff. Okay. And we said that we have a wave function of a molecule. And what did that wave function initially depend on?
R1, R2, R3.
Right, which are, what are those things?
Position of the electron and
Yep.
of the nucleus.
So this is electron, and then we had big R. And what were these things?
Position of the nucleus.
Yep, positions of the nucleus. Okay, then we said we were going to do the Born-Oppenheimer approximation. And what does the Born-Oppenheimer approximation say?
Electrons move very fast compared to the nuclei.
Yep, so electrons move very fast. And so we can say we really only have to pay attention to the electrons, and we can split apart our wave function of our molecule into a portion that is just relies on the electrons and a portion that relies on the position of the nuclei. Right, and that's as far as we got, I think. Okay, so now I'm going to write some terms out. We're going to write out the Hamiltonian for the system, and I want you to identify what each of these terms are. What are they describing? So, the Hamiltonian for a molecule is, we got H hat summation to N negative H bar squared over 2M A equals 1 N to M.
Can you adjust your camera a little bit?
Oh, yeah. Does that work?
Yeah.
Okay.
All right, thank you.
All right, we're gonna have to squeeze a lot in. We're gonna run out of a little bit of space soon. E squared 4 pi epsilon naught RIA. I J is greater than I, and E squared 4 pi epsilon naught Rij. And then finally, double summation. I was doing so well. There we go. AI, BA, MM, BA, ZB, E squared, 4 pi epsilon naught, RAB. Whoa. Okay. Let me know when everybody's done with that last term. And we're going to zoom out and we're going to look at each of these things.
Does that say M or mu? I'm just making sure. On top of the summations to the very right.
Those are meant to be capital M's.
Okay. Just checking.
Yep. Okay. Am I all right to zoom out?
Yes.
One side.
Okay. So what we're going to do next is we're going to look at each of these terms and see what are they trying to describe. Okay. All right. Let's get the whole thing in there. Okay. This first term, oh, we should put first term, what do we got here?
Kinetic energy.
Yep, it's a kinetic energy. How'd you know that, Tara?
I don't know.
Any symbols or anything that give it away?
The negative h squared over 2m.
Yep, we've seen that a lot. And then this, the Dorito or
There we go.
that gradient. This is a kinetic energy. And it's a kinetic energy of what?
The electrons.
Yep. Okay, this term. First thing is it attractive or is it repulsive?
Attractive.
Because it's energy lowering. How'd you know that, John?
That's minus.
Get that minus sign out front. Okay, what is this?
Attractive energy of the electron to the nucleus.
Yep. So it's a Coulombic attraction. Between electron and nucleus. The next term. Attractive or repulsive?
Repulsive.
How'd you know, Josh?
Positive side.
Yep, positive sign there. Okay. So what is it?
Electron repulsion.
Yep. And finally, that last term.
That one's nucleus repulsion.
Yep. Got nucleus repulsion. Okay, now what we can do, if we make the Born-Oppenheimer approximation, our lives become a little bit simpler. Which of these terms is going to change or be modified based upon the Born-Oppenheimer approximation?
The last one.
Yeah.
Yep, that last one. This last one, all that happens to it is it just becomes a constant. You figure out where the nuclei are, you see their distances, you just add up those energies. So we can rewrite our Hamiltonian in terms of E. So this is sometimes called the electronic Hamiltonian, where all we do is we kind of ditch that last term. So we get negative h bar squared, 2m, summation.
What?
I know, quantum mechanics man, right? oops, A. Four pi epsilon RIA plus N I J, which is greater than I. Okay. So this is known as the electronic Hamiltonian. And it gives the what's called the electronic energy. So we've made an approximation where we just look at the electronic Schrodinger equation, the electronic Hamiltonian. It spits out our electronic energy and our electronic Hamiltonian back out. So these are things that only depend on the electrons. They do not depend on the nuclei, which is an approximation. Now, how did these relate back to the actual energy or the total energy of the system? Am I okay to move this up a bit, like up to here? Does anybody need this thing anymore?
Oh, no, I'm good.
Okay. Okay. So, which is related to that total energy? Okay. So now let's say we wanted to get to the total energy. We have the electronic energy. How would you go from that electronic energy back to the total energy? What term did we leave out?
It's the nucleus term of
Yeah.
light repulsion.
Yep, we left off that nuclear repulsion. And the nice thing is you can actually do this. You don't have to do a quantum chemical calculation for that portion. You can just say the distances are this far away. The nuclei are not behaving as quantum chemically as in some other situations, and you can just total that up. So if you guys look in the output in some of the calculations you've done in lab, what you should see is like an electronic energy that's being reported. And if you look through the output, you can find a total energy that's being reported. And that's what the difference is between the two. One is just looking at the electronic portion, and then the total energy is adding up all that stuff. Okay? All right. So we have the Hamiltonian now of a molecule. That makes our lives easy because we can evaluate an energy, because we always want to get an energy out. But now we want to try to find a model that we can look at bonding with. So we seek to find a qualitative model of bonding. And the easiest system we're going to start with a diatomic molecule. That's the easiest one to investigate. So look at a simple system. Of a diatomic molecule. And we're going to leave those atoms generic with atom A and atom B. Okay, so now we want to think of ways to write out the wave function. We need a wave function for this molecule. What approximation could we make to come up with a simplified version of this wave function? What have we done when we looked at molecules like in inorganic chemistry? I think that's the only place we've used this approximation so far.
Mine's blanking out right now.
That's okay. Long semester, man. Ooh. LCAOMO model. So LCAO, do you remember what that stands for?
Lowest.
Orbitals.
Lowest something atomic.
It's linear combination.
Oh,
Yeah.
yeah.
Linear combination of atomic orbitals. Okay, so what the hell does that mean? So let's say we have a wave function of our molecule AB. What's that going to be comprised of?
The orbitals of molecule 1 with their like contribution.
Okay, and contribution.
A by A, contribution B
Yep.
by B.
So these are the orbital, or they're the, we're going to say basis functions to be a little more formal. So we'll make two other approximations. We assume a minimal basis where we only have one AO on each atom. And these AOs are normalized. So we assume those two things. So this would be the basis function. On A, and this is the contribution of that basis function. Now, can someone tell me what is a basis function?
It's more of just like a mathematical way to represent like each part of it, I guess.
Yeah, so when you say part of it, what do you mean?
Part of the atomic orbital to like make up like each interaction.
Yeah. So it, like you were saying, it's the mathematical formulation behind describing those atomic orbitals. So that's all a basis function is. So even though it isn't exactly true, what we can kind of pretend is that our basis functions are the atomic orbitals. You can think of them as interchangeably for now. That's not formally true, but that's what we're going to go with. Okay. So now we have a wave function, we have a Hamiltonian, we'll want to get an energy out. So let's consider the expectation value. For the energy I don't know why I wrote of the molecule. And we're gonna put that energy as epsilon. So, and what E is? This is the energy of the approximate wave function. Okay, so we have an approximate wave function. We made all these approximations. This is where we get to. Now, how do we denote an expectation value again?
Psi absolute value of psi squared.
That is
Oh, no. That's
normalization.
how would we say, like caret value, like opposite.
Yeah. Caret
Greater
operator
than-
caret. Okay. So what does this mean?
It's going to be the, yeah, just the integral of I star, and then I don't think there's an operator, or is there an operator?
There is an operator for energy, right? What's the operator?
It would be just the whole Hamiltonian.
Yep.
H squared over 2m. Isn't that? Oh, wait, no.
No, we're just going to put
Like
H in
total.
there. We're not going to write this stupid thing. We're not going to write it out 20 million times. We're just going to say H. H hat.
Okay.
Okay. And then what else do we need?
Regular phi and dt.
Yep. Okay. So now we're looking at for our molecule. And we're going to go with the electronic Hamiltonian. So that's generally how we've solved for expectation values in this class. But when I originally introduced expectation values, we had another thing in the bottom. Do you remember what we had in the bottom?
It was divided by the integral of just psi detail. Is that right?
Yep.
That just so if like you didn't have any normalized functions.
Yeah. And formally, this is the way it's defined. Okay. So now let's plug in what we have for our molecule. We have this as our wave function. Let's plug that into this expression. Okay. So get integral CA phi A CB phi B star H hat electronic CA phi A plus CB phi B d tau, all divided by CA phi A CB phi B complex conjugate CB IB d tau. Right? So all we've done is we've plugged in our LCAO approximated wave function into these wave functions, right? Okay. Let's split this apart. What we're basically going to do is we know the Hamiltonian is a Hermitian operator. What does that mean for us?
It won't equal 0, something like that, maybe.
Yeah, it's something about ones and zeros, and I'm equaling it.
Probably.
Oh no, that's orthogonal. Orthogonal.
Yeah, you're right.
Hermitian means you can kind of move. You like, for example, if you had psi I operator psi j, that should be equal to.
Oh yeah, that's what I'm thinking of.
Yeah, but like the way we test for it would be like by doing that and figuring out if it actually still equals 1.
Right. So you can show that this is Hermitian. We're not going to, I'm lazy. You can show it. So what we're going to do then is we're going to multiply CA, phi A. We're going to square this essentially. Okay. So if we do CA star plus CB phi B star times CA phi A plus CB phi B. We multiply that out, what are we going to get?
Spoil it.
What? What?
So
Yeah, you just spoil
we're
it.
multiplying this out,
Yeah.
just like you would for, like, let's say,
Wait, so where did that come from?
we'll talk about where that comes from in a second.
All right, sounds good.
Okay. Basically, we're multiplying this bottom. It's like we're multiplying this bottom part together.
I'm confused where the X came from.
This is just something different. I was trying to
we're
explain.
just saying it's just like foiling.
Right
We're just,
there.
it's really
Yeah,
like
it's foiling. I was just trying to show, like, if you could solve this, right? I want you to do the same thing for this guy.
So technically our contribution's the same, but the like phi or the whatever that is, isn't the same.
Right.
So it'd be like CA squared times phi A star times phi A.
So why do you have one that's written as phi and the other one that's written as theta?
I shouldn't.
Oh, all right. I'm like,
I
when
see
you're
if we're paying attention.
It turns out, all right, yeah.
Sorry, I was looking at circles. Yeah, so that's the first term. What's next?
Where we just get to, I mean, depends. I guess you do CA B, CA, and then phi B times or 5A, just keep it alphabetical, times phi B star, star on the B one.
Mm-hmm.
I mean, I guess it doesn't really matter. And then plus, and it's going to be CA, CB, and then phi A star, phi B, and then CB squared, and be phi B star phi B.
Yep.
Can we just convert those like contributions into just a simple constant? Do we have to write them out as CA and CB?
We want to keep them as CA and CB, and it'll be clear soon. What we're going to do too, we're going to combine these two values, or these two terms, right along in here. So we get CA squared phi A star phi A plus CB squared phi B star phi B plus 2 CA CB. We'll do phi A star phi B. Okay. Now what we're going to do is we're going to plug this expression back into this guy. So let's do the denominator first because that will be easier.
How did you get the 2 CA CB?
So what we're going to do is we're going to assume the complex conjugate doesn't really matter
Okay.
right now, just for simplicity's sake. So the bottom is going to become CA, oops, darn. We're going to scoot over that. Comes CA squared integral phi a d tau. What's the next term going to become?
Plus CB squared integral of phi b star phi b d tau.
Yep. And then we got that last term, right? 2CA CB integral.
So why'd you make A star but not B, I guess, in that case? Because
Why did I pick A as the star?
yeah.
Because
Because-
it came first. That's all. Okay, now the top part. How are the two integrals going to be, or excuse me, how is the numerator and the denominator going to differ?
The top will have H bar or H hat.
Yep. Yeah, top one will have H hat wedged in between each of these basis functions. So it's the A star, IA, H hat, A d tau, CB squared integral, B d tau plus 2CA CB integral A B d tau. Okay, does anybody see any way we can simplify this?
I'm hoping things cancel.
Everything cancels. It's 1. It's field
Yep.
count.
Things are 1, yeah. Things do cancel sometimes in PChem. You just got to get lucky. This integral. Remember, they're normalized.
It's 1.
Yep. This guy,
1.
1. And we do the same thing with this one.
No, because they're different.
Right. They're different. The other thing is we have not said that they are orthogonal yet. We have just said that they are normalized. Okay. So instead of writing this thing out 10 million times again, we're going to come up with a shorthand on how to express like this portion. So we will write these integrals as shorthand. So we're gonna come up with a shorthand notation for this. Basically, Hij is equivalent to the integral I star Hj. So we're going to shorten an entire integral. We're just going to express it with Hij. Okay, so let's rewrite our energy expression. Let's rewrite this thing. What's it going to look like?
CA squared.
CA squared, yep, times what?
HA.
Yep, AA we're going to put. Next term.
CB squared.
Yep. H what?
BB.
Yep, BB. CA, CB, last term.
2
AB.
C.
Yep, AB. And then the bottom, we got CA squared plus CB squared plus 2 CA CB integral phi A phi B d tau. Okay, and now what we're going to do, we're going to come up for a shorthand with this guy. So the integral of integral a star b d tau is called the overlap integral. Which we're going to label SAB. Okay. So what we will do next is we're gonna draw pictorially like what is SAB describing. Okay. Am I all right to move this up?
Yep.
Okay. So the overlap integral is a quantitative.
Back to that last thing written for 1 second.
Yep, this thing.
Oh, okay. Yeah, I'm good.
Okay. So the overlap integral is a quantitative measure of the overlap between the AOs. So what we're going to do is we're going to draw kind of a plot. We're going to have position along here, and on the y-axis we're going to have amplitude. We have the position of, let's say we're looking at a hydrogen molecule. Oops, we got HA, and we have the nuclei HB. Does anybody know what the atomic orbitals are going to look like? Like if I just plot their amplitude as I move in the X direction, let's call it.
What are you moving?
Mm-hmm.
Are you curve?
We are just moving through space. And we want to know.
And then what is amplitude describing? Yeah.
It's like the
Amplitude.
wave function itself.
Yeah, it's the square of the wave function. So let's pretend it's like a slice of the probability density or the radial distribution function.
So would it just be like upside down parabola type look?
Yeah, yeah, sort of. Where's the maximum going to be?
Right above it.
Yeah, right above it. So it looks somewhat like this.
Okay.
Okay, and then it should be mirrored over here, which I did a bad job of. What is there? And this portion where the two overlap, that's described by SAB. That overlap integral. Okay, so SAB, it must be greater than 0 in order to have a chemical bond. So it's a measure of the overlap between the atomic orbitals. Okay. So therefore, our energy expression, or approximated energy, is equal to Ca squared HAA plus Cb squared HBB plus 2 CA HAB, all divided by Ca squared plus Cb squared plus 2 CA SAB. where SAB again is that overlap integral. Okay, so now we have an expression to find an energy. But we have some problems here. What issues do we have right now?
We can't solve this.
Yeah, we can't solve it. We don't know what these basis functions are. We don't have values for this. But we do have a way we can figure something out. We're going to try to minimize this energy. If we use the variational principle, which we talked about last class, we can get the smallest energy that we can possibly find. And that's a benefit to us because we know, based upon the variational principle, we're either going to get an energy that's higher than the actual system or the energy of the system. So now we use the variational principle to determine a minimized value of E. Okay, so how was this done in practice? First, we need to differentiate with respect to each of these coefficients. So we're going to differentiate with respect to A and respect to B. So we need to differentiate based off of those coefficients. We're going to set that differential. If we're trying to find a minimum, what are we going to set that differential to? Or how do you know you've arrived at a minimum, like on a potential? Yeah, it's going to be equal to 0. So set expression to 0. And then we solve for CA and CB. Ooh, yelling at me. We're almost done. Okay, so that's about all the time we have 5 minutes left. We can talk a little bit of how to do this. Then we're going to be stuck halfway
We
through
have
something.
what we need done for the daily problem.
I don't know. Let
Well,
me
we
check.
also have a Quizlet. So that's more
Yeah, you do have a Quizlet, but I can modify.
That's a
it
fair
to
point.
Quizlet.
I did not think about that. Are we done with Quizlet material then?
Maybe.
Oh man.
We'll see.
Wait, maybe. Say Wednesday.
Yeah, today is Wednesday. Yeah, I mean, we are done with what we're done. We can't do any more. But you guys already had 32. Let's see. 33. Okay. You can do it. You should be okay.
Doesn't sound very convincing.
I am a very convincing individual.
He's like, you can do it.
Yeah, you got it. So that's as far as we need to go for right now. We have how many more classes left? 2?
3?
3?
When we have 3 next week?
Well, we have Quizlet, and
Oh.
then we have 3 next week.
Do we end Thursday, not Friday?
We end Thursday, though.
Oh,
We
shit.
have 2 left.
2 left after the Quizlet.
Wow.
We made it, guys.
That's
Almost
crazy.
there.
That's crazy. That's
So does anybody have any questions about what we did here? Basically, everything we did was to try and find this expression to get an energy, and now we're going to use the variational principle to get the lowest energy we can, and hopefully the correct wave function / contributions of those basis functions.
So could you ask us that question on the Quizlet?
I could. Nothing, oh, you mean like derive all this?
No, like that question you just asked.
Yep, I could.
Okay.
Wait, ask for like how would we calculate the contribution though? I'm not. We haven't. We just
Oh,
used-
like how? We're gonna go through how on class on Monday.
Oh, okay.
You just have to know why you're doing these things.
Oh, well, that's just about as tough. So
Yeah. Okay. Any other questions? Okay.